Hi everyone, my name is Robert Hesse and I work for Cerebras Systems. Cerebras is a startup that was founded in 2016 by a handful of computer and system architects with a mission to change the compute landscape for deep learning. And we've since been very successful. We've seen one of our talks at HopChips in the past 2 years. And the company has grown to over 200 people in 2 locations now. One is in Los Altos in California, where I am, and then we have a new office in Toronto in Canada. And in fact, we've doubled in size since I joined last year. So we're still growing and hiring. So if you like what we do and would be interested in working with us, please reach out. Today, I'm going to be talking about the Wafer scale interconnect in our Wafer scale engine. First, I'm going to talk about deep learning as a workload and why Wafer scale is a good idea in that context. Next, I'll cover some of the architectural details of our Wafer scale engine. Then I'll dive into some of the challenges that we encountered along the way while building a chip at that size, especially those pertaining to the interconnect. And lastly, I'll cover some of the details of the underlying communication fabric, the Wafer scale interconnect. So why deep learning? First of all, because deep learning is arguably the most important workload of our time. For the past couple of years, we've seen it proliferating with enormous success across industries and applications, such as vision, speech, language, recommendations, and probably many more. It's already very pervasive, and we use it every day when we interact, for example, with chatbots or buy something on Amazon, or think of self-driving cars that are on the road even today. And the exciting part is that we've probably only started scratching the surface of what's possible. So while all of this is exciting, a lot of things are still changing in the field. But one thing is definitely certain, and that was mentioned by Benjamin before. The amount of compute required is increasing at an exponential pace. And predictions are that the growth in compute demands will continue this way for some time. For example, a recent study by OpenAI shows that between 2012 and 2018, basically going from AlexNet to AlphaGo Zero, compute demands have increased 300,000 fold. And the scale being used here is petaflops per second days, which means that even very capable systems like NVIDIA's DGX2 with 2 petaflops per second, for example, takes weeks or months to train the latest models. And what this basically shows is that this is a compute problem that requires resources that are far beyond the capacities of a single traditional device. So traditionally, what happens when we want to use multiple compute devices to solve such massive problems is that these devices get all fabbed together on a single wafer as separate die. And then they get cut up and packaged into individual chips. Subsequently, they get connected again with enormous efforts using off-chip interconnects in data centers, as Ben has mentioned. So at Cerebras, we decided to do things a little differently. What we do is we leave the wafer intact, not cut it apart. Instead, we're using on-chip wires to connect the individual die back together. And this audience probably knows better than anybody else that using on-chip wires instead of off-chip wires comes with enormous benefits. We see 1 to 2 orders of magnitude higher bandwidth, 1 to 2 orders of magnitude lower area and power, and 2 to 3 orders of magnitude lower latency when compared to off-chip interconnects like NVLink or InfiniBand or PCIe. And building a chip this way at wafer scale resulted in the following. This is our chip, the Wafer scale engine. It's the largest processor chip ever built using a single piece of silicon. It's over 46,000 square millimeters in size. That's bigger than a dinner plate. and is the first chip that contains over 1 trillion transistors. We're at 1.2. All that is powering 400,000 independent AI optimized cores. And the raw numbers are just impressive by itself. We have 18 gigabytes of on-chip memory, which compares to usually tens or hundreds of megabytes. We have 9 petabyte per second of memory bandwidth, which is orders of magnitude higher than traditional bandwidth to off-chip memory. And that allows us to keep all the 400,000 cores utilized without caches or a memory hierarchy. And last but not least, we have 100 petabit per second of aggregated fabric bandwidth. And like I said, the numbers are impressive, but what that allows us to do is really to run very large deep learning models locally on a single chip at cluster scale performance. Architecturally, this is a 2D mesh of 400,000 fully programmable processing elements. Each of the processing elements is actually an independent, fully programmable processor with its own flow control, registers, memory, etc. It's true MIMD. And they can either all work independently, or a workload can be parallelized and distributed across all the cores, where each core works on part of the problem and the results get communicated back across the fabric. And each of these processing elements is from the ground up designed for deep learning. First, the central component to any core is its compute. And our compute is fine-grained, fully independent, and programmable. And while it has ML-optimized instructions for linear algebra operations, which are the most common and basic instructions in neural network compute, we kept it flexible enough to perform any kind of computation. And that really makes it ideal for the changing neural network field with constantly changing model architectures. It has built-in hardware data flow mechanisms to enable dynamic execution, which allows us to take advantage of sparsity acceleration. And a lot of neural networks, as you probably know, are very sparse, which means they have a lot of zeros, which we don't really want to do compute on. The second key component is the memory, and our memory is all fully distributed on-chip SRAM, which is local to the cores. We don't have any globally shared memory. And what this does is it avoids the bandwidth and latency bottlenecks of traditional off-chip memory. Going off-chip always poses some sort of bottleneck, and we don't have that because all of our memory is on-chip. And as you probably know, conventional architectures rely on caches and data reuse to get around these bottlenecks and to still provide high utilization. Unfortunately, the fundamental operation in neural networks is a matrix vector multiply, which has no data reuse. So caches don't really work. And to deal with this, the community has developed a technique called batching, which Ben also alluded to earlier, which uses matrix multiplies instead. And while matrix multiplies do have data reuse, there are other trade-offs related to accuracy, for example, which Ben also mentioned. So with our memory architecture, which has high enough bandwidth to keep the cores utilized without data reuse, researchers can actually explore those trade-offs without performance penalties. And we're able to enable high utilization and small batch sizes, much higher than was possible with traditional memory architectures. And finally, it's critical for a deep learning optimized architecture to have a high bandwidth and low latency interconnect. Our fabric spans across the entire wafer with the same performance everywhere. And that's only possible because of wafer scale integration. Because all these cores are connected on chip, on silicon with no wires. That's how we get the performance. And the fabric enables all 400,000 cores to operate together as a single massive chip and collaborate to solve a single neural network problem. So this slide provides a few more details regarding our support for sparsity. It's enabled by data flow scheduling and hardware, where computation in the cores gets triggered by data from the fabric. So the idea is that only when data arrives from the fabric does the computation get kicked off with an instruction lookup and subsequent scheduling of data path cycles. And if no data arrives from the fabric, no compute is triggered. And what this allows is that is intrinsic sparsity harvesting. It just comes out of this architecture. If the sender doesn't send any zeros by filtering them out, the receiver's compute will not be triggered for those unnecessary calculations. So not only does that save power because we perform no wasted work, but we also get, excuse me, we also get acceleration by immediately skipping to the next useful work and skipping everything that's not useful. Sorry. Of course, there were also a few challenges along the way, and some of them were related to how to just physically and logistically handle a chip of that size. For example, mechanical stress due to thermal expansion becomes a problem. There are also no standard packages or sockets that you can just plug this into. So we had to figure out how to connect it to a PCB and develop our own power and cooling solutions. But two of the challenges stand out as fabric related in particular. So I'm going to cover them in a little bit more detail. The first one, maybe most obvious challenge when it comes to wafer scale, was cross-die connectivity. We build our wafer exactly like any other wafer with independent die. Because standard fab processes actually require all the die to be separate. And we couldn't invent a new fab process, so we're using that same process and have the die separate. But what we do, instead of cutting up each die into individual chips, we basically cut out the largest square possible on that wafer. However, that doesn't make the die connected. The standard process has scribe lines which separate each die. And those are usually used as mechanical barriers for the die cutting, as well as for test structures during the fab process. To fit into the standard process, we actually don't touch any of that. But what we do is on top of that, in partnership with TSMC, we add wires to bridge the scribe lines. And this allows us to extend our 2D mesh across die. And by doing so, we achieve the exact same connectivity that we have between cores across the scribe lines. And we're creating a homogeneous array all the way to the wafer scale. And those wires are actually very, very short, way less than a millimeter in length, which allows us to drive the bandwidth very high at low latency. If you think about it, driving a millimeter on silicon is relatively trivial compared to driving through PCBs, cables, and connectors that a traditional interconnect might have. The second challenge was yield. Yield is a major challenge even for non-wafer scale big chips today. So it would be impossible to yield an entire wafer without any defects. And standard silicon process defects, they're there, no matter how mature the process is. You just have to deal with it. You cannot get rid of them. And the picture shows an example of what those defects may look like on a die. In this case, we have two defects. But since we have so many die, there's going to be more than 2 defects. So here our solution really is redundancy. Redundancy is your friend when it comes to yield. What enables this is the uniform small core architecture that we have. Enables us to use redundancy to address yield with very low cost. What we have is our design has redundant cores and redundant fabric links, and we use the redundant cores to replace any defective cores. And then we use the redundant fabric links to reconnect everything to restore the 2D fabric. And that's shown in the picture on the right. The dark yellow cores are regular cores, and the light yellow on top are the redundant cores. And on the left, with no defects, the redundant cores are unused to just sit there. However, if there is a defect, as shown on the right, we use the redundant core to replace the defective core. And then we use the redundant fabric links to reconnect everything to a logical 2D grid. And this is all done in hardware and not exposed to software. Software always sees a fully homogeneous 2D mesh. Before we move on to the fabric details, let's recap the advantages of wafer scale compute for deep learning. The compute capabilities are massive, more than can fit on a traditional single die. It's optimized to efficiently accelerate the most common neural network operations and exploit sparsity for additional performance gains. And because the cores are fully programmable, as mentioned before, it's flexible enough for future developments in the deep learning field, which is constantly changing. The memory is large enough to fit entire models on chip, and it provides enough bandwidth to allow for high utilization, even with small batch sizes. And on top of that, the fabric really is a key enabler for efficient wafer scale compute. In order to take advantage of parallelism, by distributing the workload across all the 400,000 cores, it needs to provide high bandwidth and low latency to remove any communication bottlenecks that usually impede the scaling of DL. So traditionally, the scaling across devices poses significant communication challenges, as was part of Ben's talk. And most of the efforts in GPU scale out, for example, are actually spent in trying to minimize communication. With a high bandwidth fabric like ours, these challenges go away and seamless scaling basically becomes possible. So that leads to the interconnect part of the talk. So in order to provide a fabric that is really capable of this, we developed the wafer scale interconnect. And what it is, it's a network on chip that's purpose built from the ground up for deep learning applications at wafer scale. Therefore, the design was primarily guided by deep learning application characteristics and the wafer scale requirements. So if we take a look at the application characteristics, a few things stand out. The first thing is that most data communication is local, and that's because deep neural networks are deep, which means they have multiple back-to-back layers as pictured on the right. And those layers usually only communicate with their adjacent layers. Even in more advanced networks with skip connections, for example, the communication is still relatively local. There's also no globally shared memory that would require global communication. All the data is kept local to a neuron. So there's really a fundamental property of neural network communication that is local. And they also exhibit a static communication pattern where the model structure, as defined by the ML researcher, defines the exact communication pattern, both the routes and the amount of data that is being communicated between all the nodes. And that communication structure is known a priori. So we know all the bandwidth and all the routes in the network ahead of time. What that means is that the network really only needs to support a static subset of communication paths and bandwidth allocations for a particular application. They change between applications, but for a particular application, it doesn't change. And that's very much in contrast to the many-to-many communication we see in traditional general purpose architectures. So our network on chip should probably be taking advantage of this. In a deep learning model, there's also a large amount of fan-ins and fan-outs, which is caused by each neuron either transmitting or receiving its activations from a whole set of other neurons. And two more properties that we talked about before are Dataflow and Sparsity. In a neural network, there's really no control or memory addresses that need to be communicated. It's just data, which are activations in this case. And those are being transferred between layers. And just like in our brain, not every neuron fires all the time. In fact, they fire very rarely. And that's why there's usually a large amount of sparsity inherent in neural networks. So all these properties are very different from traditional general purpose network on chips. So they should be taken into consideration. And in terms of requirements that come from the wafer scale integration and not from the application itself, we need the fabric to support redundancy for yield, as described earlier. And we also want to provide a monolithic view of the entire wafer, such that models can scale across die boundaries, and the compiler can basically regard the wafer as a single compute fabric without any discontinuities. It's also important that we use as few resources for the network on chip as possible, especially at this scale. Every transistor really counts. Every transistor that we use in a router, for example, or for buffering gets multiplied by 400,000 times. And it takes away from area or power that could be used for compute or memory instead. And lastly, mapping a problem of this size and enabling parallelism across 400,000 cores really requires a huge amount of bandwidth. So in the following slides, I'll go through how we address each of these requirements. First, the wafer scale interconnect at its core is built around the Dataflow architecture that I mentioned before. The fabric is fully configurable according to an application's exact data flow. And this is shown in the pictures on the right. The tall black and white graph is a deep learning model. I don't exactly know which one it is. And that gets analyzed by our compiler. And the compiler then extracts the layers and the data flow between the layers and maps it onto the fabric, as can be seen on the right with the red arrows is basically the data flow, and the dark rectangles are the layers. And this is all done at compile time. And to support this type of fine-grained data flow between the layers, the fabric was designed around transporting data at its finest granularity, which is just a single datum at a time. So we just have a single unit of transport. We don't have any large messages. We use the same unit of transport in flow control, which is just a single word of data. In the case of sparse data, we send an index along with it, but we always just send a single piece of data. So that removes a lot of the overhead that comes with message processing. So there's absolutely no message overhead, no routing information. We're really only sending data, which is a true data flow architecture. And that data, when it's being received, triggers a task at the receiver. Really one piece of data at a time. Every data arrival can trigger a task. And that's how we support sparsity, as I described earlier. So on the top right, I'm keeping track of the requirements. So this basically addresses the data flow and sparsity requirements of the workload. And in terms of the topology, we're using a uniform 2D mesh spanning the entire wafer. And this has a couple of benefits. First of all, the 2D structure matches the 2D layout of the linear algebra computations, the cores, and the die very well. It's also very efficient for local communication and provides uniform high bandwidth across the entire wafer. And this is important because it allows us to use a single software algorithm to map and scale models across the entire chip without really worrying about the die boundaries. and that's shown in the little cartoon on the right. There's a network consisting of 3 layers, the red, blue, and green. And that gets mapped onto a fabric on the right, consisting of 4x4 die. And in this case, with this particular mapping, one of the blue cores actually ends up on its own in the lower right corner of a die that's also populated with red and green cores. If die boundaries pose a communication bottleneck, this would have to be taken into consideration, and this type of mapping would probably be detrimental. Even though it might be beneficial for performance, it would not be picked. But that is not an issue if we have the uniform bandwidth that the 2D mesh provides. Also, a lot of the traditional drawbacks of mesh topology also don't apply because A, we have no local hotspots because we don't have any globally shared memory that might provide hotspots. And we can actually avoid contention completely due to the fact that we know all the communication pattern and bandwidth allocations are a priori. And that allows us to configure the fabric and provide enough bandwidth for each of the communication paths. So also the regularity of 2D helps a lot with our homogeneous redundancy scheme. So taking all of this together, the topology takes off a few of the requirement boxes, which is it's good for local communication, it's good for redundancy, provides a monolithic view of the entire wafer, and high bandwidth. Okay, in terms of routing and flow control, we're using virtual circuit switching with on-off flow control. And what virtual circuit switching allows us to do is to pre-configure routes in the fabric that can then be traversed later on without any routing overhead at all. And this is again shown on the cartoon on the right. As defined by the neural network model, which you can see there in the middle, one of the red neurons sends data to one of the blue neurons along the green path, and the top blue neuron sends data to 2 green neurons along the red path. And these routes can be analyzed by the compiler and can be configured in the fabric by statically assigning each color an output direction in every router along the path, which is shown with the green and red arrows. So whenever a message of a particular color, whether red or green, arrives at a router, it automatically takes its predefined route without incurring any routing overhead. It automatically goes that way. And the red path actually shows how multicasts are also supported with very low overhead. All it basically takes is to configure 2 output ports for a particular color, and the router then splits the data and it gets duplicated in both directions. So while this is obviously a little toy example, our software during the compile process analyzes all possible routes in a model and then configures them as static routes between producers and consumers at compile time. And that's shown in the picture on the right. Because we know all the routes at compile time, we can actually construct paths that by construction don't have any deadlocks, which also reduces the hardware requirements to deal with deadlocks at runtime. To provide enough routing flexibility, even with these fixed routes, we allow 24 virtual circuits or colors per router. And the benefits, as mentioned, are that we can support static communication pattern like they exist in neural networks with absolutely no routing overhead. No message header is necessary, and the router pipeline can be extremely simple, which reduces latency. There's also, as mentioned, built-in low-cost multicast support. On top of the virtual circuit switching, we use on-off flow control, which is basically the simplest flow control you can imagine. There's a single back pressure wire going back that says my buffer is full, and our buffers are extremely small. So yeah, because we have small buffers, we have very low buffer usage, and using on-off flow control like that actually has the additional benefit of providing implicit synchronization between producers and consumers by quickly propagating the back pressure. So because we have very shallow buffers in the routers, and there's basically a single cycle between the routers for back pressure, when the producer cannot accept any more data because it's processing a long task, it can just assert the back pressure wire, and that signals to the producer very quickly that it cannot send any more data. So if we look at the top right, that basically concludes the list of requirements that we wanted to address, with the routing and flow control supporting static communication pattern, high fan out and fan in, and really this is mostly about minimizing resource use and taking advantage of the properties of the network to do so. So to summarize, the Cerebras wafer scale engine was designed from the ground up to run deep learning at scale, with cluster scale performance on a single chip. And the wafer scale interconnect is really a key enabler for scale and performance by being purpose built for DL applications at wafer scale. It provides data flow communication at high bandwidth and low latency to keep the compute utilization high across the entire wafer and to enable seamless parallelization. That concludes my talk. Thank you very much. And even though I don't have it on the slide, we're also hiring, so reach out.